Hello and welcome everyone to the Deep Dive. Today we're going way beyond the surface level. We're digging deep, right down to the very foundations of artificial intelligence. We're tackling a massive question, one that's fascinated people for, well, ages really. But it became incredibly real, almost tangible, back in the mid-20th century. What does it actually mean for a machine to think, to reason? Is it just about, perfectly following a strict set of rules, like some kind of flawless logic engine? Or is there something deeper, more complex going on? So our mission today, it's ambitious, I won't lie, but I think you'll find it really rewarding. We're heading back in time, back to the 1950s and 60s, a really fascinating period, just brimming with this incredible optimism about AI. Back then, intelligence, well, the dominant idea anyway, was that it was all about pure logic, about following formal rules, precisely. So our deep dive today, we're calling it Machines That Reason. We're going to explore the birth of what's now called symbolic AI. We'll look at the core ideas that got it all started, check out some really groundbreaking early programs. Stuff designed to prove theorems, solve puzzles. Pretty amazing for the time. And we'll dive into those initial huge hopes. The belief that maybe, just maybe, intelligence could be boiled down entirely to formal logic. But like any exploration, right, this journey also hit some walls. It revealed limitations, cracks in that neat idea of pure logic. And that really set the stage for how we think about AI today. So get ready. We're about to unpack the very first attempts to create machines that could genuinely think. Okay, let's get into it. It's easy, living now, surrounded by tech, to think AI is just this recent thing, like it popped out of Silicon Valley Labs a few years ago. But before we even touch on modern computers, the actual core idea of formal logic, mechanical reasoning, well, its roots go back millennia, not just decades, millennia. It wasn't born in some server farm. Its earliest thinking happened in, well, ancient philosophy. It's quite a lineage when you think about it.
It really is. And what's so fascinating is just how deeply embedded this idea of logical rules is in how we even conceptualize human thought. When we try to pin down what reasoning is, we almost automatically think of a structured process, right? Step by step. And that's not just us imposing a modern view. That's genuinely how many thinkers centuries ago tried to understand and formalize it. They were trying to map out the laws of thought itself. Take Aristotle, for instance. We're talking around 384, 322 BC. He was arguably the very first to really lay out a precise set of laws for the rational mind. Not perfectly formal by today's standards, maybe, but systematic. He developed syllogisms, you know the ones, the classic examples. All men are mortal, Socrates is a man, therefore Socrates is mortal. And the really big implication there, you see, was that, in principle at least, these laws meant you could generate conclusions mechanically. Just given the starting points, the premises. It was like a blueprint, a conceptual design for a reasoning machine. Way, way before electricity, let alone computers. It was this radical notion that reasoning wasn't some kind of magic human spark. It could be formalized, broken down, maybe even automated, like thought itself could be engineered.
Wow. So Aristotle wasn't just doing philosophy in an ivory tower. He was, in a way, laying the groundwork for computational logic. Yeah. Saying, here are the rules, the mechanics of thought.
Exactly. He was essentially saying reasoning has structure, rules that can be identified and followed. And that idea, it didn't just stop there. It evolved. Moving forward into the medieval period and then early modern times, these ideas got even more ambitious. People started thinking about practical implementation. There was Ramon Lull, who died around 1315. He had this incredible visionary concept that useful reasoning could actually be done by a mechanical artifact. That's a huge leap, right? From pure theory to thinking about a physical machine performing logical steps. He even designed a kind of paper machine, the Ars Magna, with rotating discs to combine concepts. Not a computer, obviously, but the idea was there. Mechanical generation of thought.
A physical machine for logic.
Yeah.
Back in the 1300s.
That's incredible. It is. And then fast forward to the 17th century, you have Thomas Hobbes, 1588 to 1679. He pushed it even further. He proposed very boldly that reasoning was basically like calculation, numerical computation. He famously said, we add and subtract in our silent thoughts. And that wasn't just a metaphor. He was explicitly linking thought processes to math, suggesting that reasoning is like performing calculations but with ideas instead of numbers. That was a really critical conceptual jump for computation, right? Basically framing thought itself as a form of calculation, making it seem less mysterious, more like a process.
It's amazing how that thread just keeps running through history. Philosophers thinking about thought as calculation and the inventors actually building machines to do calculations.
Exactly. They ran in parallel. While these philosophical ideas were developing, the actual automation of computation was slowly getting started. Leonardo da Vinci, around 1500, he actually designed a mechanical calculator. It wasn't built then, but people built it later based on his drawings. And guess what? It worked. Then, Wilhelm Schickard, around 1623, he built what's generally considered the first working mechanical calculator. Add, subtract, basic stuff, but automated. And Blaise Pascal followed up in 1642 with his Pascaline, a more famous arithmetic machine. And connecting these dots is key. These early machines, okay, they weren't intelligent, not by a long shot, but they were hugely important conceptually. They laid the practical foundation. They showed that complex mental tasks, or at least parts of them like arithmetic, could be broken down into discrete mechanical steps, that they could be automated. They demonstrated the power of automation in a domain previously thought purely human. It made the abstract idea of a thinking machine seem, well, maybe not possible yet, but less like pure fantasy, more like an engineering challenge down the road.
So it really puts things in perspective. Long before anyone even dreamed of computer as we picture it, silicon chips, software order, the core ideas, the seeds of reasoning machines, were already there. Planted by philosophers, nurtured by early inventors, that whole deep history makes the jump to AI in the 20th century feel less like a sudden leap and more like, well, almost inevitable in a way. The ideas were just waiting for the right technology. Absolutely. And that technology arrived, didn't it? Mid-20th century. Suddenly, we have actual computing machines. Increasingly powerful ones. And those ancient ideas about formal logic, they found a brand new, very exciting home. This is when the real pioneers of AI started building actual programs, not just calculating, but trying to reason, putting that philosophy into practice.
Right. And that immediately begs the question, what did intelligence actually mean to those researchers back then in the 50s and 60s? For many of them, maybe most of them, it was really tied up with the ability to manipulate symbols according to rules, like a mathematician proving a theorem, or a logician building an argument, step by logical step. That core belief became the foundation for what we now call symbolic AI. The idea was, if you can write down the rules, you can create intelligence. So just to clarify what symbolic AI means, its central principle was that intelligence is basically rule following and problem solving, and it works by manipulating symbols. These symbols could stand for anything, really concepts, objects, logical statements. The idea was you represent human knowledge as a set of symbols and rules for manipulating them. Think about chess again. The pieces are symbols. The rules of movement are the manipulation rules. The intelligence is the logical process of using those rules to win. And this is a really key difference from a lot of modern AI, especially deep learning. The stuff that powers image recognition or language translation today. Deep learning mostly learns patterns from massive amounts of data. It figures out correlations statistically. But early symbolic AI, it didn't learn rules from data in the same way. Instead, researchers explicitly programmed human knowledge and logical rules into the system. It was about encoding what we know directly. It's worth remembering, as one source, AI Snake Oil, points out, that AI is really an umbrella term. There are lots of different technologies under it, and they don't all have that much in common. Symbolic AI is one very specific foundational branch.
Got it. So less about learning from experience, more about encoding logic directly. Almost like trying to bottle the essence of human rationality. And this led to a huge wave of optimism, didn't it?
Oh, absolutely. The optimism was almost boundless back then. There was this really widespread belief, maybe a bit naive in hindsight, but genuinely held. The belief was that human intelligence, at least the rational part, could be completely reduced to formal logic. And if that was true, then it could be perfectly replicated in machines. The thinking was pretty straightforward. If you can just define the rules precisely enough for any given task, you can program intelligence for that task. It felt like they were on the verge of cracking the code of thought itself. You hear stories about researchers genuinely thinking they were just a few more if-then statements away from creating true AI. It was an incredibly exciting, ambitious time. And this wasn't just engineering. It directly tackled huge philosophical questions. Questions like, can formal rules actually lead to valid conclusions? Or even deeper, how does knowledge actually translate into action? They were trying to build systems that could embody the answers to those questions, systems that could mimic, maybe even surpass, human logical reasoning. And this led to some amazing experiments, especially in theorem proving, that was seen as a pinnacle of logical thought. One of the most famous early programs was Logic Theorist. This was 1956, created by Alan Newell, Herbert Simon, and J.C. Shaw, giants in the field. Their goal was ambitious: get a program to prove theorems in propositional logic, that basic true-false logic.
Okay, so how did it actually do that? How did Logic Theorist work?
Well, technically, it was an inference procedure. Basically, it had a starting set of known truths, axioms, and a set of rules for deriving new truths from the existing ones. Imagine giving it the basic rules of logic and a few starting facts and then letting it run. It would methodically apply the rules step by step, trying to generate a path from the axioms to the theorem it was trying to prove. It wasn't random guessing. It was a systematic search through the logical possibilities. And it proved that computers could do this kind of abstract intellectual task. And its success was stunning. Logic theorists managed to prove 38 out of the 52 theorems in Chapter 2 of Principia Mathematica.
Wow, Principia Mathematica. That's Whitehead and Russell's famously complex work trying to ground all of math and logic.
Exactly. It was the foundational text for a machine in 1956 to wade into that level of abstract mathematical reasoning and successfully derive theorems. It was monumental. It really shifted people's thinking. It showed that maybe, just maybe, this kind of high-level reasoning could be mechanized. It was a powerful demonstration, and it fueled even more optimism.
I can only imagine the excitement. A machine proving complex math theorems. So beyond logic theorists, how do they generally approach building these logic systems?
Well, logic theorists definitely inspired more work on general theorem proving. The core idea was often built around these knowledge bases. These knowledge bases contain two main things: axioms and theorems. Axioms are your starting points, the fundamental truths you accept without proof in a given domain. Theorems, on the other hand, are statements that logically follow from the axioms. They have to be true if the axioms are true. The job of the AI system was to derive these theorems using logical rules. Now, purely logically speaking, you might think you only need the axioms. You could derive everything else from scratch, but practically that's incredibly inefficient. Imagine having to reprove basic calculus rules every single time you face a physics problem. So including known theorems in the knowledge base was crucial to reduce the computational cost. They acted like pre-computed logical shortcuts, making the systems much faster and more practical. And the architecture, how they represented the world, was also quite clever for the time. They thought in terms of states and actions. A state described the situation, both the world outside and the agent's own internal belief state. Think about a simple thermostat example used in some texts. Its internal belief might be off or heating. The environment state could be cold, comfortable, or hot. Actions, like turn on heater, had specific preconditions. Things that had to be true in the current state for the action to even be possible or applicable. For instance, a planning system for a robot might have an action like fly plane from A to B, but the preconditions would be things like the plane must be at airport A and B must actually be airports. If those aren't true, the action fails. This formalizing of states, actions, and preconditions was how they broke down complex problems into manageable, logical steps, building these decision paths.
Yeah, this is where it gets really fascinating for me. Because they weren't just talking theory. They were building real programs, like logic theorists, tackling problems that seemed to require actual intelligence. But, and there's always a but, isn't there? As they pushed these symbolic systems harder, tried to make them do more complex things, challenges started popping up. The initial shine started to wear off a bit. Yeah, it sounds like the 50s and early 60s were kind of the golden age, the honeymoon period for symbolic AI. This is an amazing feeling that they were really onto something huge. But then, reality started to bite. As researchers tried to scale these ideas up, apply them to messier problems, they started hitting some serious roadblocks. That beautiful promise of pure logical intelligence. It started showing some cracks. Disillusionment began to set in.
That's a really good way to put it. And it brings us to that crucial question. What happens when the clean, elegant world of formal logic meets the messy, complex, unpredictable real world? The answer, sadly for those pioneers, often involves something called the combinatorial explosion, and also some pretty fundamental limitations in the approaches they were using. It was a tough realization. The combinatorial explosion, that was a major headache. Imagine you're trying to plan a trip with just a few choices for each leg. Manageable, right? Now imagine adding more destinations, more transport options, more timing constraints. The number of possible combinations doesn't just add up, it multiplies exponentially. Very quickly, it becomes astronomically huge. Early symbolic AI systems constantly ran into this. When trying to solve problems or prove theorems, the number of possible steps or logical paths they had to search through just exploded. Every new factor, every extra rule dramatically increased the search space, often making the problem computationally intractable, even for the computers of the day. And this failure, this inability to really come to grips with the combinatorial explosion, was a major criticism of AI. It was a key point in things like the Lighthill report, which had big consequences later. It showed that while logic worked great for simple, well-defined puzzles, scaling it up to real-world complexity with all its variables and uncertainties was just incredibly difficult using those early methods. Douglas Hofstadter even connected this kind of search problem in formal systems to finding patterns in numbers involving unpredictably long searches, chaos among the integers. It pointed to a deep, almost fundamental computational barrier. It wasn't just about faster computers. The methods themselves struggled with scale.
That's a really clear explanation. The sheer number of possibilities just became overwhelming. Like trying to map out every single grain of sand on a beach that keeps getting bigger. Was there a specific moment or a particular technology that really highlighted these limits?
There definitely was a very significant moment, and it involved a different approach that initially seemed very promising, the perceptron. The perceptron was developed by Frank Rosenblatt in the late 50s, early 60s. It wasn't symbolic AI, it was an early type of neural network, inspired by how brain cells might work. And initially, there was huge excitement. Rosenblatt was quite vocal, the media picked it up, and it was presented as a potential basis for general intelligence, for machines that could learn like brains. There was even a mathematical proof, the perceptron convergence theorem, which sounded great. It basically said that if a problem was solvable by a simple perceptron, the learning algorithm would find the solution, which fueled the hype. But then came the critique. Marvin Minsky and Seymour Papert published their book Perceptrons in 1969. And it was devastating in many ways. They rigorously proved that these simple single-layer perceptrons had severe limitations. They showed they could represent very little. The classic example they used was the XOR problem, exclusive OR, basically telling if two inputs are different. A simple perceptron physically cannot learn this basic logical function.
XOR. Why was that so important? Why couldn't it learn that?
Think of it visually. A simple perceptron can basically draw a single straight line to separate different categories of data points on a graph. For simple logic like A and D, output is 1 only if both inputs are 1, or OR, output is 1 if either input is 1, you can draw one line to separate the yes points from the no points. But for XOR, output is 1 only if the inputs are different. One is 1, the other is 0. The yes points, 0, 1, and a 1, and no points, 0, 0, and 11, 1, are arranged in a way that you just cannot separate them with a single straight line. Minsky and Papert proved this mathematically. It showed a fundamental limit on what those simple networks could represent or learn. And the impact of that book was huge. Even though Minsky and Papert themselves noted their critique did not apply to more complex multi-layer networks, a really important caveat, the message that got out was basically perceptrons don't work. As a result, research funding for neural networks just dried up almost completely, dwindled to almost nothing, as one source puts it. It essentially killed off most research into connectionist AI, the neural network approach, for well over a decade. The critique was widely taken as discrediting the whole idea, even though it was technically only about the simplest types of perceptrons. It really cemented the dominance of symbolic AI for a while and delayed progress in other areas.
Wow. So a single powerful critique, even if maybe misinterpreted or overgeneralized, basically shut down a whole avenue of research for years. That's incredible. So combinatorial explosion, the perceptron critique, was there a sort of official verdict on AI's progress around that time?
There was. Things came to a head with the Lighthill report in 1973, particularly in the UK. Sir James Lighthill, a very prominent mathematician, was asked by the British government to evaluate the state of AI research. His report was highly critical. It really hammered home that failure to deal with the combinatorial explosion. It argued that AI hadn't delivered on its big promises, especially in areas like machine vision or understanding language. It basically said the field had overhyped itself and the methods weren't scaling up. And the government reaction was pretty drastic. Based largely on that report, the British government decided to end support for AI research in all but 2 universities. It wasn't just a small budget cut, it was a major withdrawal of funding across the board in the UK. And this really marked the start of the first proper AI winter. Funding dried up not just in the UK, but elsewhere too. Researchers left the field. Public perception cooled significantly. That early, boundless optimism really hit a wall. It showed how vulnerable research funding can be to perceived failures and critical reports.
An AI winter. Sounds silly. So we had this initial dream of building these grand general-purpose reasoning machines, right, like logic theorists aiming for universal logic. But then these massive problems hit. It sounds like maybe the focus shifted. You mentioned earlier that later AI successes often came from being more specific, not general. Was that a direct reaction to these failures?
Precisely. That's a really key insight. The early dream was very much about general-purpose algorithms for reasoning and problem solving. One size fits all intelligence. And look, those general methods are still important. They're part of the toolkit. But the big lesson learned, often the hard way, was that later, more practical, successful AI applications gained much of their practical power from applying specific knowledge to specific domains. It was a pragmatic response to the combinatorial explosion. If you can't build a system that knows everything, maybe you can build one that knows a lot about one thing. So instead of trying to build a general thinker, researchers started developing what became known as expert systems. These systems were loaded with huge amounts of very specific, human-provided knowledge about a narrow field, like diagnosing certain medical conditions or analyzing geological data for oil exploration. They weren't intelligent in a general sense at all, but they could perform incredibly well, sometimes better than human experts, within their tiny niche. Why? Because their knowledge base was deep and specific, avoiding that massive open-ended search problem. So there was this real tension between the grand vision of universal logic and the practical necessity of using domain-specific knowledge. Reality kind of forced a narrowing of ambitions, at least for a while. Sometimes being less general meant being more useful.
So summing that part up, the initial incredible excitement around machines that could reason using pure logic definitely hit a harsh reality check. The sheer scale of real-world problems, that combinatorial explosion, plus the demonstrated limits of some early approaches like simple perceptrons, it all led to a major slowdown, a period of disillusionment, the AI winter, a necessary maybe but difficult reevaluation for the whole field. Thinking about this whole story, the rise and then the stumble of early symbolic AI, it really makes me wonder how much of that difficulty was purely down to the technology they had back then. Slow computers, limited memory. And how much was it about something more fundamental, like maybe our basic understanding or definition of intelligence itself was part of the problem? Were they aiming at the right target even? It feels like more than just an engineering issue.
That's a really insightful question, and it hits on something that's still incredibly relevant today. It's very possible, looking back, that the way early AI was framed so heavily focused on logic, on rules, on this idea of universal reasoning might have inherently limited its own progress. Because a key thing to remember is there's never actually been one single, clear, agreed-upon definition of what artificial intelligence is, and that ambiguity matters. AI is often described now as an umbrella term, covering a whole range of loosely related technologies. There's just no consensus about what is and isn't AI, so how can you definitively say you've achieved it if you can't even agree on what it is? And this isn't just academic navel-gazing. As the Atlas of AI points out, how we define AI is doing work. It sets a frame for how it will be understood, measured, valued, and governed. For example, if you define AI primarily as something more reliable than humans, that pushes towards trusting it in critical situations, maybe too quickly. If you define it only by technical benchmarks, you might ignore the huge energy costs or societal impacts. The definition shapes everything that follows.
That makes a lot of sense. How you define the goal changes the entire race. And it seems like that early definition, focused so squarely on logic, maybe missed some crucial parts of what makes us intelligent.
Exactly. And that leads to a huge realization about human intelligence. It's definitely not just logic. Not even close. The human mind isn't like one big general-purpose logic processor. It's much more complex. Marvin Minsky, who we mentioned earlier with the perceptrons critique, later developed this idea in the Society of Mind. He argued the mind contains hundreds of different types of machines interconnected in specific ways. Specialized systems for vision, for language, for motor control, for social understanding, physical intuition, all working together, sometimes competing. Minsky believed the power of intelligence stems from our vast diversity, not from any single perfect principle. Humans use many effective, although imperfect, methods. Our thoughts and actions emerge from conflicts and negotiations among societies of processes within the mind. That picture, messy, diverse, emergent, is radically different from the clean, unified, logic-based view of early symbolic AI. It highlights things like common sense, intuition, context, maybe even emotion stuff that's incredibly hard to capture in formal rules. And this connects to an ongoing debate. What level do we need to simulate to get intelligence? Do we need to model every neuron, every chemical reaction? Probably not. Most agree we don't need to replicate the brain molecule by molecule. We can likely emulate higher levels of organization. But where exactly that line is, how much biological detail or architectural complexity is necessary, is still a very open question. It underscores just how deep the challenge is. We're still figuring out what intelligence is fundamentally.
So looking back at this whole journey into early symbolic AI, it's about much more than just old programs like Logic Theorist or technical problems like combinatorial explosion. It's really about this fundamental ongoing challenge of defining intelligence itself, and realizing how our assumptions about what intelligence is directly shape the kinds of machines we try to build. Those limitations they hit back in the 50s and 60s, they weren't just technical bugs. They were really philosophical speed bumps, revealing how big the gap was between formal logic and the messy reality of human thinking. So today we've taken quite a deep dive, haven't we? We traced artificial intelligence right back to its logical roots, exploring that crucial era of symbolic AI in the 1950s and 60s. We saw how ancient philosophers like Aristotle laid down concepts that centuries later fueled the dream of mechanical reasoning. We felt that initial wave of excitement around programs like logic theorist machines actually proving theorems from Principia Mathematica. And we understood that powerful belief that intelligence could just be a matter of getting the logic right. But we also saw the other side of the coin. We looked at those critical turning points, the points where reality pushed back. We talked about the combinatorial explosion, how the sheer complexity of problems overwhelmed those early systems. We examined the impact of Minsky and Papert's critique of perceptrons, exposing limitations that, rightly or wrongly, contributed massively to the first AI winter. That period of doubt and reduced funding, reinforced by things like the Lighthill Report. And through it all, I think we learned some really valuable lessons. Lessons about the huge difference between problems that fit neatly into logical boxes and the sprawling, ambiguous complexity of intelligence in the real world. Those core challenges that symbolic AI grappled with. How do you handle ambiguity and vast data without explicit rules? How do you scale? How do you even define the goal, intelligence, in the first place? Believe it or not, these are still questions echoing in the AI landscape today. They inform everything from the giant language models to the predictive algorithms that shape our world. So here's a final thought to leave you with. As we build these incredibly powerful new AIs, often based on learning statistical patterns from data rather than following explicit logical rules, ask yourself this: are we truly moving beyond the fundamental hurdles faced by those early pioneers? Or are we perhaps just encountering new, more subtle variations of the same deep challenges? Complexity, scale, the nature of intelligence itself just wearing a different technological disguise. Something to think about. Thanks for joining us on the Deep Dive.